Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to talk about how to figure out the mole fraction of the product of a reaction that happens once the reaction goes to completion, as well as figuring out what the volume of the piston is after the reaction. So we're dealing with a movable piston here. So let's get into this. So in this problem, we have nitrogen gas, N2, reacts with hydrogen gas, H2, to form ammonia gas, NH3. You have hydrogen and nitrogen gases in a 18.0 liter container fitted with a movable piston. The piston moves so as to keep the pressure inside the container constant. Initially, the partial pressure of each reactant gas is 0.5 atmospheres. Assume that the temperature is constant and that the reaction goes to completion. Okay, so that's the setup there. And they want to ask us to calculate the mole fraction of the ammonia in the container after the reaction goes to completion. And then they also want us to calculate the volume of the container after the reaction has gone to completion. Remember, we're dealing with a movable piston here. So if the pressure changes, the volume, the piston can go up and down, and so the volume can change. Okay, so the first thing we need to do is we need a balanced equation. So let's go ahead and write that. So we have nitrogen gas, N2, plus hydrogen gas, H2, and that's going to give rise to ammonia, NH3, gas. And so balancing the equation, I have two nitrogens here. I only have one here, so I'm going to need a 2. So now I have 2 nitrogen on both sides. And now the hydrogen, so I have 2 times 3 is 6. I have 2 here, so I need a 3 here. So now I have my balanced equation. Okay, that's the first thing. Now the next thing, we need to figure out the relationship between the information they gave us, or the characteristics of gases that they gave us. So here, it's important to keep in mind that they told us, where is it at? Oh, temperature is constant. So that's important, temperature is constant. And we know that the start of the container is 18 liters, and we're told that the piston is going to change in order to keep the pressure inside the container constant. So pressure is constant and temperature is constant. So how does that help us? Well, if I write out the equation for the combined gas law, right, that's going to be P1 V1 over T1 N1 equal to P2 V2 over T2 N2. So here's my the combined gas law equation. So this is really the only equation you need to know. All the other equations come from this, because you can get the equation of the gas law that you want by eliminating anything that's constant from this equation. So for example, we know that we're told that temperature is constant. So temperature is constant. So we'll eliminate temperature from the equation. So T1 and T2 are gone. And we're told that the piston is going to fluctuate or go up or down in order to keep the pressure constant. So pressure is going to be constant here as well. So P1 and P2 are gone. And here we're left with V1 over N1 is equal to V2 over N2. So if I rewrite that here, V1, pressure is eliminated. So V1 over N1 is equal to V2 over N2. And so what this tells us is that volume and the number of moles of the gas are directly proportional to each other. So notice that we have V1 over N1, that's a ratio. If I start with a certain number, a certain amount of volume and amount of gas, then if I change that, if I change one of these, the other has to change so that the ratio that I get between the new volume and new amount of gas, that ratio is the same as the original ratio. So in other words, if I double the volume, then to keep the ratio the same, I have to double the amount of gas. So notice that the 2's are going to cancel out and I end up with the same ratio that I had before. So why is that important? That's important because that means that volume is proportional to the amount of gas. So I can treat the unit of volume as if it was moles. So N represents moles of gas, volume represents the volume. So for the units of volume, whatever units of volume I have, that's going to be related to the moles. So I can treat volume units like I would moles. And because I have a balanced equation that has mole ratios, well, I can use the unit of volume as mole ratios. So I can use volume ratios in the same way that I have mole ratios here. So the coefficients can be used as volume ratios, just like mole ratios. So that's going to be helpful in answering the first question. So I just wanted to kind of go over that to explain how that works. So now, what information do they give me? So they say that the initial partial pressures of each of the gases is 0.5 atmospheres. So what I can do is I can do the reaction first and assume that there's no change in volume, right? Because we want to keep the volume the same and just deal with pressure changes. In the same way, if I keep the volume constant, right? If I just assume that the volume is going to be constant for the reaction to go to completion, and then the next step is to say, okay, once the reaction is complete, we're going to have a new pressure there, but then to change the pressure back to where it was, the volume has to change. So it's a kind of a theoretical or two-step problem. This really is happening all at the same time. This isn't really what happened in reality, but to make the problem simpler, you kind of have to take it theoretically or mentally into two different steps. So here, in the same way, I'll do it again. I have P1 V1 equals T1 N1 equals P2 V2 over T2 N2. In this case, we'll assume that the volume stays constant and the temperature. So in this case, the temperature is going to leave, and we'll say the volume stays constant for the time being. So during the reaction, we're going to keep the volume constant. So in this case, then pressure and the amount of gas is going to be proportional. So I can use the pressure as if I was using the same as moles. So the mole ratios can be pressure ratios. So that's what we're going to think about. That's the way we're going to deal with the first part of the problem. So part A, pressure is going to be proportional to moles. So they're giving me pressure. Each gas has a pressure of 0.5. So I'm going to do my ICF table. So initial, change, final. So I is the initial pressures that I begin with. So they're telling us we're starting with 0.5 atmospheres for each. So 0.5 atmospheres. And I start with 0 atmospheres of the ammonia. Now I have to figure out the change. They tell us that this goes to completion, so one of these is our limiting reagent. Which one? We have to figure out which one is the one that's going to go away first. Which one's going to run out first? That's the limiting reagent. So to do that, there's a couple ways you can do that, but I think for this problem, we want to convert one reactant into another to see how much of that reactant we need. So I'm going to take nitrogen, this amount of nitrogen, how much of the hydrogen do I need to react completely with 0.5 atmospheres of the nitrogen? So how much hydrogen do I need? It's a 1-to-3 ratio. So I'm going to use that as a conversion factor. I'm going to use that as a mole ratio, but in this case, it's going to be a pressure ratio, right? So here, I'm going to start with 0.5 atmospheres over 1. And this is atmospheres of N2, so I'm going to put N2. And so for every 1 atmosphere of nitrogen, I need 3 atmospheres of hydrogen. So I'm going to use that as a conversion factor. So on the bottom, I'm going to put 1 atmosphere of nitrogen and 3 atmospheres of hydrogen. So atmospheres of nitrogen cancel out. Now all I do is I take 1.5 multiplied by 3, and that's going to give me what? That's going to be 3.5. Basically, it's 1.5. So half of 3 is 1.5 atmospheres of hydrogen. Which makes sense because if this is 1-to-3, then if this is 0.5, then I need 3 times as much. So if I add 0.5 together 3 times, I get 1.5. So I need 1.5 atmospheres of hydrogen to react completely with the nitrogen. But I only have 0.5. I do not have enough hydrogen to react completely with this amount of nitrogen. So I'm going to run out of hydrogen before I run out of nitrogen. So this is going to go away. This is going to be depleted first. So this is my limiting reagent. So hydrogen is my limiting reagent. Okay, so what that means is I'm going to run out of hydrogen before I run out of nitrogen. So this is going to go to 0. So my final amount at the end is going to be 0 atmospheres. So I'm not going to have any hydrogen left over. That means that I lost 0.5 atmospheres. So how much nitrogen did I lose? Well, to figure out the amount of nitrogen I lost, I need to use the 1-to-3 ratio. So let's go ahead and do that again. So this time, I'm going to start with the 0.5. So 0.5 atmospheres of hydrogen were used up. I want to find out how much nitrogen was used up. So I got to use the 1-to-3 ratio again, but this time the 3 moles, I'm sorry, not 3 moles, 3 atmospheres, they behave like moles. So 3 atmospheres of hydrogen on the bottom, 1 atmosphere of nitrogen on top. So atmospheres of hydrogen cancel out. Now I'm going to take 1.5, divide that by 3, right? So basically it's going to be 1/2 multiplied by 1/3, or divided by 1/3, same thing, or divided by 3. And in this case, it's going to be 1/6. So 1/6 atmospheres of nitrogen were used up. This is the amount of nitrogen that was used up. So this is going to be a minus 1/6 atmospheres. And so we have 1/2. So if I take 1/6, oops, wrong way. I want to take 1/2. If I take 1/2 and subtract 1/6, well, I need the denominators to be the same. So 1/2, that would be the same as 3/6, right? So now I have 1/2, I have 3/6. So 3/6 minus 1/6 is going to be 2/6, which is the same as 1/3. So I have 1/3. I'll put it down here. So I have 1/3 atmospheres of nitrogen left. Okay, so if I started with 0 atmospheres of product, well, how much product did I form? Well, it's the same thing here. So I have 1:2 ratio, right? So here, if I lost 1/6 of nitrogen, then I gained twice as much over here. So losing 1/6 over here is the same as gaining 2/6 on this side because it's a 1:2. You could also do the conversion factor, right? We can do the conversion factor again. So if I have 1/6 atmospheres, ATM atmospheres of N2 over 1, and it's a 1:2 ratio, so 1 atmosphere of nitrogen on the bottom, 2 atmospheres of NH3 on top. So 1/6 times 2 is 2/6, or 1/3 again. So I gained 1/3 atmospheres of the ammonium, so therefore the final pressure of the ammonia is 1/3 atmospheres. So that is what I have left. So the nitrogen that's left is 1/3 atmospheres. The amount of ammonia that's produced is 1/3 atmospheres of pressure. So let's go back to the question. So calculate the mole ratio or mole fraction of the ammonia in the container. Well, since pressure and moles are proportional, we can treat the mole fraction as a pressure fraction, right? So now that I have 1/3, I'm going to erase this. And so what's 1/3? So a mole fraction here, right? So the mole fraction, that's going to be equal to the number of moles of NH3 divided by the total moles. But that's going to be the same as the partial pressures, right? So that's going to be equal to the partial pressure of NH3 divided by the total pressure. Well, what's the partial pressure of NH3? 1/3. What's the total pressure? 1/3 plus 1/3 is 2/3. So all we need to do is take 1/3 atmospheres, divide that by 2/3 atmospheres. Atmospheres are going to cancel out. So 1/3 divided by 2/3 is going to be, what is that going to be? That's going to be 1/2. Because dividing by a fraction is the same as multiplying by its reciprocal. So if I multiply 1/3 by 3/2, the 3's cancel out, right? So if I multiply by 3/2, the 3's cancel out, and I have 1/2. So I have 1/2. So that is the mole fraction of ammonia after the reaction has gone to completion. Okay, that's part A. Now for part B. Now we can allow the piston to adjust to go back to the original pressure, right? So now the pressure is going to be the same, whatever that was to begin with, it doesn't matter. And so now the volume's going to change, okay? Now we know that volume and the number of moles are proportional. So we can use our oops, not P1. So in this case, V1 over N1 is equal to V2 over N2. Okay, so the moles that we started with, that's going to be proportional to volume, right? So here we have the volume. What was the volume? So our initial volume. So we're going to have to label. So V1 is going to be equal to the original, that's the original volume, so 18.0 liters. And then for the moles, and what are the moles? Well, again, we can use the pressures as proportional to the moles, right? So here we were told that each gas before that reacted was 0.5. So we had two gases, 1 and 2, 0.5 and 0.5. So the original number of atmospheres is a total of 1. So this is going to be, so our number of moles we'll say is 1 atmosphere worth of moles, right? So we can treat atmospheres as moles. And then before or after the reaction, so before the reaction, it's 1 atmosphere is going to be proportional to the moles. And then after, we said, is going to be 1/3 plus 1/3. So after the reaction, this is the new pressure, right? So then we can add that together. And so we got that. And then for N2, that's going to be 2/3. So that means N2 is equal to 2/3 atmospheres or moles. If you want to think of it this way, instead of atmospheres, we can do moles. And then V2 is what we want to look for. So V2 is a question mark. So then we just plug this in. So our V1 is going to be, it's 18.0 liters over 1 atmosphere or mole. I'll do atmosphere / mole. Okay? And then that's going to be equal to V2, which we got to look for. And then our final number of moles or atmospheres is going to be 2/3. So 2/3 atmosphere / mole. And so when you multiply, you cross multiply and divide, you're going to get V2 is equal to 12.0 liters. So that is the new volume, because the piston has went down because the pressure, the total pressure decreased. So then the volume decreased. So the piston went down. Oops. Sorry about that. So the piston went down because pressure decreased, and so the volume decreased as well. That's it for this video. I hope you enjoyed the video. If this helped you in any way, if you enjoyed the video, then please by all means like the video, share the video, hit the like button somewhere here. Also, do me a favor, subscribe to my channel, help me out. Also, when you do that, click on the notification bell, click all also, so you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, or if you have a topic, put that down below. I would like to do that for you. Thanks for joining me, and have a great day.